Brilliant. Okay, so I was going to start the webinar today by welcoming Professor Lubo Jankovic, a distinguished expert in building energy performance and carbon reduction, as our guest speaker. Professor Jankovic is the Professor of Energy and Buildings at Energy House Labs at the University of Salford, where his innovative research focuses on improving building energy efficiency and sustainable retrofitting. His widely acclaimed work, including the Designing Zero Carbon Buildings book series, has significantly shaped the industry. With groundbreaking contributions such as non-invasive experimental measurement methods for building retrofit, quality control, and reducing performance gaps in hempcrete buildings, Professor Jankovic is at the forefront of sustainable building innovation. So yeah, very excited. He's a chartered engineer, a member of prestigious organizations like CIBSE, ASHRAE, and IBIPSA. And he's currently a distinguished lecturer with ASHRAE over the past 2 years and currently. So we're really, privileged to have you speaking today, sharing your insights and expertise. We are recording this webinar, and as you're obviously aware, the UKAEE, we're the UK chapter of the Association of Energy Engineers, where we're dedicated to advancing the scientific and educational interests of fellow professionals in the energy industry, while also fostering direct action on sustainable development. So our mission is to create a consistent, fair and engaging platform for existing AEE members with the central organisation, certified professionals here in the UK, and really anyone who's interested in the resources and the different offerings around the AEE here in the UK. We're really, we have been reactivated over the last year or two. We're always looking for volunteers to help us grow and progress. Currently, we do have a opportunity on the board as a secretary. So, if you're interested in making an impact and helping us lead around the organisation in the UK and bring it to the next level over the coming year, we'd really be interested in hearing from you. If you want to join our mailing list, you can reach us through team@ukaee.org. So or reach out directly to myself on LinkedIn or Mark or Darren. So that's an introduction there. So Lubo, if it's okay with you, I'll hand it over and we can get into the webinar.
Yes, brilliant. Thank you very much, Brian, and thank you for a great introduction. I really appreciate it, and also welcome everyone. What I'd like to do is talk to you about experimental building research under controlled conditions at Energy House Labs. So experimental building performance research is, in my view, essential for improving design methods, tools, and control approaches. And in situ field measurements are expensive and often subjected to disruptions, delays, uncertainties. And typical field performance monitoring is conducted over 2 years. And this represents a long lead time before results are fed back into design process. And short-term tests, such as co-heating, are disruptive for occupants and can be affected by changing weather. And before my tenure at Energy House Labs, I lost count of how many buildings I monitored, probably over 100 buildings as part of field trials. But one project in particular that I'm showing here involved 20 houses in Swindon and 20 houses in Norfolk. And there were various complexities of fabric and systems issues and interactions with the occupants. For example, air tightness was far worse than design. Heat pumps were not installed correctly and were producing suboptimal results, and people didn't know how to operate them. And in terms of other issues with occupants, we had an occupant switching a mechanical ventilation with heat recovery system without us knowing about it. There were occupants who didn't know how to switch the heat pumps off. But in one case, an occupant managed to switch off our weather station that happened to be in his garden. So all of this required frequent site issues and visits, and it is expensive, especially if you think that these sites are probably maybe about 4 hours drive apart, and then a third site is where I live. So in terms of short-term monitoring, such as co-heating tests, these require stable weather over a week or more. And I did a co-heating test in this particular house at the BRE site, and this building was given to me to work with in March of that particular year. And this co-heating test was likely to be disrupted by sunny weather, and I had to install reflected foil as a precaution to prevent excessive heat gains into the building. So therefore, we need to do something better than field trials, and we are in a race against time to understand and mitigate the effects of global warming. According to Copernicus Global Climate Highlights, the average global temperature in 2024 was 1.6 degrees Celsius above the pre-industrial level. This is almost breaking news as of a few days ago. And this has breached the Paris Agreement threshold of 1.5 degrees Celsius. And in 2022, the Met Office recorded a new record temperature of 40.3 degrees Celsius in Lincolnshire. So an accelerated approach towards building performance research is needed to achieve net zero targets by 2050. And such a new approach has been developed at the University of Salford Energy House Labs. So what are Energy House Labs? We have 4 labs plus another one potentially emerging. We have Energy House, which opened in 2012, and then Energy House 2, which opened in 2023, and then Thermal Measurement Laboratory and Smart Meters, Smart Homes Laboratory. And we are just about to establish a modeling lab that actually takes data from all these other labs and generalizes it, scales it up, and adds value to the data. Okay, so what is Energy House? According to Climate Change Act of 2008, UK carbon account for the year 2050 has to be at least 100% lower than the 1990 baseline. And existing homes will be still standing, 70% of these will be still standing in 2050. And retrofit solutions are difficult to assess. Field trials are difficult and expensive, and we need to be able to repeat experiments. And we need to have the ability to change the building, even to build in defects and take more risks. So Energy House is fully furnished, fully instrumented house within a climate chamber. And it is a semi-detached house in a controlled environment. It has high data quality with more than 300 data points, not just to evaluate performance, but the underlying reasons for the performance. And the environmental chamber and the house are summarized here. There are 3 heating systems in Energy House. There's gas, there's air source heat pump and electric heating. Then there's obviously hot water heating. It's fully furnished. There are appliances there, and it's fully automated. So the doors, windows, bath, shower, lights, and heating are fully automated. And it is constructed using methods found in between 1900 and 1910 in the UK with reclaimed materials, and it is a solid wall construction. The chamber allows for -12 degrees to +30 degrees external temperature, and then there are wind and rain and solar radiation simulations and snow. We can produce dynamic and steady state conditions, and these can be programmed to follow given weather patterns. So in Energy House, we can conduct full retrofit. We can conduct full retrofit without floor insulation. We can do just solid wall insulation. We can investigate performance of different glazing types, change the loft insulation. We can do acoustic tests, or we can just use it as a reference case. Now, I'll give you a few examples of research results that were achieved over the past 7 years. A small one of 0.6% of saving if central heating boiler is controlled to control the start time and the ramp times of heating, and chopping sessions of heating. And if we remove air dissolved in the system, in the central heating system, that contributes to a saving of 0.5%. But if we add time proportional and integral thermostat, that provides the savings of 32%. If that thermostat is integrated with thermostatic radiator valves, that leads to a saving of 53.5%. A voltage optimization system was introduced to change the voltage down to 220 volts, and that improved performance between 3.3 and 3.9%. Water-filled electric heaters were also tested against gas central heating. Savings are generated because there are no boiler heat losses, no losses to floors through distribution, and there was quicker to heat and cool. There were no lag times. The saving was 23.4% annually. And then underlay, typical carpet, saved around 3% of energy. Then installation of a window film on a single glazing effectively created double glazing, which changed energy saving, improved energy saving by 2.8%. Curtains, when used at night, 2.2%. Suspended timber floor insulation, 7%. Hybrid wall insulation, so that external wall was installed to gable and rear walls, and internal wall insulation to front elevation to main facade, so that the main facade was kept untouched. And that created savings of 45%. Loft insulation top-up from 100 to 270 millimeters, 3.8% of saving. Window replacement to A triple plus generated 7% of savings, and full fabric retrofit 63%. Okay, so Energy House is therefore very useful to evaluate all these different performance issues. We can push it and poke it and see what happens, but this is a fixed asset reflecting 20% of UK housing, and it has a limited weather profile of between -12 to +30 degrees Celsius. Waiting time in Energy House to do any new experiments can sometimes be more than a year. And we've had approaches from other universities, and therefore to do experiments, and therefore Energy House 2 was created as a new facility to retain leadership in the approach. So Energy House 2 opened in 2023, and it has two large climate chambers which can maintain temperatures between -20 to +40 degrees, which represents 95% of the populated areas on Earth. There are wind and rain and solar radiation and snow additions. We have a proper alpine grade snow machine, and dynamic and steady state conditions are possible, can be programmed. We have vehicle access to allow for bidirectional charging to homes. There are PV and gas source heat pump and air source heat pump and hydrogen supplies. And we are working with our partners in acoustics and social science. So I'll run this video and just show you how it was developed. There are two chambers, two detached houses can be constructed per chamber. Temperatures of -20 to +40 degrees. Solar radiation starts from 500 nanometers and peaks at 1500 nanometers. We can produce 250 millimeters of snow per day, rain 200 millimeters per hour, and wind up to 17 meters per second, which is around 38 miles per hour. These are large plants that service the energy house too. So these are heating, ventilating, air conditioning, cooling plants. And the house was, energy house 2 was constructed as I said, in 2023. Now the chambers each contain 1200 millimeters deep soil. So there's a pit under each climate chamber, which is 1200 millimeters deep, filled with soil, isolated by thermal insulation from the ground beneath and surrounding pit. And the walls and ceilings of the chamber are well insulated, providing isolation from the external climate with high levels of air tightness. Both chambers are independently conditioned by large heating, ventilation, and air conditioning system. And in addition, there are weather rigs. And these provide additional climatic effects. So this is the time-lapse record of the construction process in the environmental chamber 1, where both Belway Homes House and Saint-Gobain Barrett E-Home 2 house are constructed, and they are aligned with Future Homes standard. So here is just a photo of environmental chamber 1 under snow with a car inside. So this just gives you an example of what is possible to simulate. So Future Home Standard will happen in this year, in 2025. And it involves 75% carbon savings reduction compared to 2013. houses are zero carbon ready. They have efficient fabric, more airtight. They will have lower running costs. They will have solar PV, batteries and EV chargers, and air source heat pumps. There will be no gas heating. Energy House 2 has 2 real homes, Saint-Gobain and Barat E-Home 2 and Belway Homes House, which are very similar to Future Homes standard. So these are the houses of the future, effectively. Now, the Future Home Belway has a timber frame construction with infrared panels in the ceilings. There's a PV inverter and a battery in the loft. There's mechanical extract ventilation. There is hydro-top air source heat pump. There's mechanical ventilation with heat recovery. There's wastewater heat recovery system based on Myra heat capture integrated tray, which is 34 to 40% efficient, and Myra heat capture vertical pipe system, which is 58 to 64% efficient. There are infrared wall panels. There are precast insulated concrete planks, underfloor heating, the radiators, convection radiators, ductwork installed for future cylinder trials, so not necessarily used immediately, but there for future trials. And there's also aqua air source heat pump. And there are various measurements that we conducted here, such as whole house heat loss measurement. Then apologies, my mouse is very sensitive and it just jumps to different slides. Okay, so whole house heat loss was measured using co-heating test, QUB test, and Veritherm test. These are 3 different tests. U values were measured using ISO 9869 standard, and air tightness testing was measured with blower door and also with pulse test, and thermographic survey was conducted during the blower door test. For co-heating, if we do field trials, we need to account for solar radiation, and that kind of trial takes 2 to 3 weeks, and it's a quasi-steady state. You can't achieve steady state, and it is this equation is correct for solar radiation. But for energy house chambers labs, the heat transfer coefficient is calculated using a much simplified equation, and takes 3 to 5 days, and its steady state condition is achieved, and solar radiation is omitted. So U values were measured over a period of 3 to 5 days under steady state conditions. These are the locations, wall locations where the heat flux plates were mounted, and you can see values. You can see the numbers corresponding to U values in these particular locations where the heat flux plates were located. So from point 12 to point 19. So when you, for example, design a building and say, I want U value to be 0.12, you never know whether this is going to be consistent across the wall, and this is why we measure these things. And you can see that there are differences of the U value between different points on the wall. Okay, then air tightness was measured using fan pressurization with pressure difference of 50 pascals. So this is a blower door with a very powerful fan, And that allows for thermographic survey and air leakage detection. I've done these tests many times myself in the field trial situation before I joined Energy House Labs. And when you put a building under negative pressure and at 50 pascals, that allows air to come into the building, and that is then very good opportunity to go with a thermal camera and see where you have air leakage. And in many cases, I found air leakage from unexpected places, such as electricity sockets, for example. Now, the pulse test achieves pressure difference of 4 pascals, and this is quite similar to natural ventilation pressures such as wind effect and stack effect, and these are rapid tests. Okay, so co-heating tests produced these results. So this is the heat transfer coefficient, which was on this scale between 82.8 and 82. And the design was just under 80. And this was the grid power is in orange here. It's 1.3 kilowatts. Okay, now, so the results here of the heat transfer coefficient using 3 different tests, co-heating, QUB, and Veritherm, are shown here between 76.5 and 85.6 watts per Kelvin. And you can see results of the air tightness here. With blower door test, air permeability was 4 cubic meters per hour per square meter. With a pulse test, it was 3.25, but design was 2.5. So it was really underperforming in terms of building was really underperforming in terms of air tightness tests. And then air change rate was almost 4, under blower door test 3.23, under pulse test, and then we had corresponding heat losses here. So, and then U values were also measured, and we just had to take for doors and windows, we had to take U values as provided by the manufacturers. But for the fabric, we measured our own U values, and there were differences, for example, between design and build. 15.82 as designed for external walls with 25 millimeter service zone, and 14.93 for the as-built situation. So these are heat losses, but U values were in fact 18 for design, and 0.18 for design, and 0.17 for the as-built situation. And in other walls where there was external, where there was 38 millimeters service zone, 0.18 U value as designed, and 0.17 as built. Rendered walls were quite similar to design and build, and ceiling was quite different because the insulation in as-built situation was disturbed by the contractors, and it was much worse. 6.5 was heat loss comparing to 4.18. heat loss in watts per Kelvin, but U value, design U value was 0.09 for the ceiling, but 0.14 for the for as built. Okay, and patio doors were based on manufacturer's data provided. So design versus measured, heat transfer coefficient. You can see here that measured for the fabric is 67.9 and infiltration was another 14.3. So that is just over 80, but design was under 80. And heat loss by components, openings were exactly the same as designed because values were used from the manufacturers because only the center pane could be measured. And then walls design for walls was 21.6, but measured 20.6. Floor was 5.1, and ceiling was 4.2 for design situation, and floor and ceiling for as built was 6.5. So the whole house heat loss was therefore 7.7% worse than the design. The air tightness of the home was 61% worse than design. The loft insulation was disturbed, as I said, by the site operators, and was not as intended. So it was underperforming by 56%. The windows and doors generally performed as designed. The floors generally performed as designed, although this was very difficult to measure. So overall, the Bellway home performed well. Air tightness could have been improved. Remember, design was 2.5 and as built was 4. So the house builders must stick with these houses for the rest of the work. And this is not just in this particular case. I mentioned earlier that I monitored a large number of houses in field trials. This pretty much corresponds to my experience, where air tightness is typically lower. I was carrying out air tightness tests in a newly constructed estate of houses, and as I was coming in with a gear, with my fan and blower door and all that gear into the house, a site operator was coming out with a mastic gun and saying to me, "I've made it ready for you, mate." And I went in and I found a hole in the window frame, so I had to call him back to actually fix that before I could do the air tightness test. So these are kinds of things that a level of detail that needs to be paid attention to actually get houses airtight and to perform to design specification. So there were many service penetrations in this house, and that contributed to the worse air tightness. The house was full of sensors and cables, and loft installation was not quite how it was intended to be. And there were also some issues around sealing of joints at the ceiling to wall interfaces. So both houses had these issues. But in general, it was reasonably good performance. We measured actual performance of the building under controlled conditions in the chamber, and we examined the air tightness, the efficiency of the elements at retaining heat, air leakage paths using thermal imaging, and how efficient the house was at retaining heat. So both houses in the chamber performed well in terms of how they lost heat. Past trials have actually found gaps of up to 150% of discrepancies between measured and designed values. And according to the database at Leeds Beckett University, this is the co-heating database for new build homes. Dwelling number 23 had a gap of 140%. And if you look at all these different dwellings, they had quite considerable gaps. But this is the future home, the Bellway house in our Energy House lab. 8% is the gap, which is 7.7, but rounded up to 8. But eHome 2, which is also in the same climate chamber, was even better, 4% gap between design and as built. We also do testing of heat pumps for domestic hot water delivery, and thermocouple sensors are installed at tap outlets. So this is in the kitchen, this is bathtub tap, and this is the bathroom sink tap. And these are two heat pumps that we tested. One was Valent, one was Curve. Valent was actually delivering heating to the whole house, but also had hot water heating, domestic hot water heating function, whereas Curve heat pump was just for hot water heating. And we used large tapping profiles according to a British standard. So this large tapping profile was a worst case scenario. So for every hour of the day, we had to draw a certain amount of volume of hot water and certain amount of energy. And tests were conducted in a series of 72 hours under climate conditions of 5 degrees, 7 degrees, and 14 degrees. And everything was automated. So if you would go into the house, suddenly this tap would open and run for a while and close, and then another tap would open and run for a while and close. And this then enabled us to look at delivery patterns and find out whether these heat pumps can actually deliver enough hot water according to the British standard. And so these are temperatures, hot water temperatures delivered under 3 different tests. And this is hot water consumption volume during 72-hour tests. And we found that actually these heat pumps can deliver the required amount of hot water according to the British standard. We also do computer modeling and optimization, and the aim of this study was to address discrepancies between design and as-built values of a new built future home standard house in climate chamber 1. So this is the Bellway house. And we investigated design optimization, focused on envelope U values, walls, loft, windows, French doors, air permeability, and also heating set points for living and other zones. Now, how did we do that? We took measured values for external walls and loft and ceiling and various other parameters, and so these are shown in bold. And then we went below and above these as a kind of guess situation. Would performance have been better if if the U value was 0.16 rather than 0.17 and so on. And we put all of this into multi-objective optimization engine of the simulation tool. And when we count all these different scenarios, so there's 9 here, there's 8 here, and so on, and we tested different set point temperatures. We found that the total solution space was just under 4.5 million possibilities. So that then goes into a simulation that takes several hours, and then we get back the results. And the results are provided in the form of scatter plots, where the red points are called points on a Pareto front. So these are the points that are the closest to the origin of the coordinate system. So these are the optimum points. And here we have two scatter plots, one without a restriction to discomfort hours, as shown here, but one is restricted to 400 discomfort hours. So discomfort hours are here on the vertical axis, and heating electricity is here on the horizontal axis. And then what we can do here is see which points fulfill our design criteria. For instance, if we want to have a higher number of discomfort hours, maybe towards 400, then we spend less amount of heating energy. But if we spend more on heating energy, then we have less number of discomfort hours. So this Pareto front is effectively a design decision-making tool which enables us to take trade-offs between different design options. We also have been looking into measurement of building physics properties, and you've seen that there are measurements of heat transfer coefficient, but I personally have been doing this in a slightly different way. I've been running a calibrated model of the simulation model of the building from the climate chamber 1, and then heating that up to something like 45 degrees in the model and letting it cool down, and finding out the time constant, and then that enables me to calculate heat transfer coefficient. And time constant is the time that it takes the building to go through 63% of change from starting the heating to achieving the endpoint, achieving equilibrium. So, and both for cooling and heating and cooling, time constant is the same. So if the time constant is the same, and time constant is effectively capacitance divided by heat transfer coefficient, then heat transfer coefficient has to be a variable. And you can see here that heat transfer coefficient starts from something like almost 1000 watts per Kelvin, and goes down to the measured value measured by the co-heating test. So we're looking into this and trying to find out what actually makes the heat transfer coefficient to be variable, or what is the causal relationship between heat transfer coefficient and its variability. So to address this and other building physics properties, we are running 2 separate investigations: hardware-based machine learning and software-based machine learning. And hardware-based is based on this gadget which I developed, which is now installed in one of the buildings. So this is in a conservatory in climate chamber 2. And this shows you heat transfer coefficient of the conservatory. This is a sensor that measures daylight and movement and temperature, and another one is like another sensor like that is outside, and then a heater is operated by this control device to actually maintain temperature and calculate heat transfer coefficient. And we also do software-based machine learning. So this house in chamber 2, which is called the vector house, we take data from that, and using this bespoke in-house developed model of a genetic algorithm, where we start assessing how close the predicted value is to measured value using random numbers, and then we reduce the randomness by checking the errors of these random numbers and crossing them over, just like it happens in genetics, and also mutating them. And then we get different heat transfer coefficients calculated daily. So this is work in progress, and there'll be more to report about that in the future. So future research will be based on ongoing analysis of heat pumps to deliver domestic hot water. There'll be physical experiments with heating up and cooling down of houses. There'll be measurement of heat transfer coefficient, time constant, and effective thermal capacitance, determination of effective solar apertures under an artificial sun irradiation, overheating analysis and mitigation measures, ongoing measurements of the heat transfer coefficients for control purposes, and scaling up of the value of experiments using computer modeling and simulation. So to conclude, experimental building research is a prerequisite for improving energy performance and achieving net zero, and field trials are expensive and often subjected to disruptions, delays, and uncertainties. There's a time delays, and uncertainties regarding the achievement of net zero targets, and climate chambers at Energy House Labs provide controlled conditions that reduce the time and cost of field trials and increase the accuracy of the results. For example, instead of running 2-year field trials, we could do the same in 2 to 3 weeks and achieve results that are representative of field trials. So the research at Energy House Labs contributes towards the achievement of net zero targets in a timelier manner and with more certainty. So just to acknowledge the contributions from the following of my colleagues who worked on the facilities and/or materials for this presentation: Professor William Swan, Professor Richard Fitton, Dave Farmer, Grant Henshaw, Dr. Christopher Tsang, and Dr. Kay Q. My name is Lubo Jankovic, and here are the contact details, and thank you for listening, and I'll be happy to answer questions.
I'll jump in then to maybe start off. That was really, really interesting. Thank you for that. So just in terms of my day to day as an energy manager and trying to propose business cases for energy conservation measures, as we call them. The first, I think, on the the second and third slide, you had a table which was sort of summarizing, for different retrofits. You might present these sorts of savings. So I thought that was really interesting because as an energy manager, you're trying to sell something and a saving, and you sometimes have to do a rough calculation. If you do this, you'll get a certain percentage. Is that table available, to the public? And would you suggest that those sorts of percentages are more relevant than some of the benchmarks that you might find in SIPC guides and ASHRAE guides and things?
I would say that these are the most up-to-date results, most up-to-date benchmarks, because SIPSI and ASHRAE benchmarks are based on longer-term performance, and this is pretty much like historic performance. It's not up to date. So I would trust our numbers more than ASHRAE and SIPSI. But I'm a member of both ASHRAE and SIPSI, so yes. They might shoot me for saying that.
No, good stuff. And just a couple of details then. A discomfort hour, you had a measurement there, discomfort hour. What could you just describe what that relates to?
Discomfort hours. Discomfort hours. How many? So in a simulation of a building conducted over a period of a year, which has 8,760 hours. A year has 8,760 hours. So this is a simulation duration in terms of time steps. So 400 hours of these 8,760 hours are considered to be discomfort hours. We limit the simulation to take into account only the results below the discomfort hours threshold. So discomfort hours of 400 is just several days that people may experience discomfort. So this is a number chosen by the research team to see what we are getting in terms of results under these comfort constraints.
Great. We have Les Bruce here, who's put a comment in saying, excellent presentation, great piece of research for moving forward, but half the battle may be the on-site construction, Bellway homes, etc. Other than talking the talk, are they getting it right on-site regarding labourers, clerk of works, etc., to ensure the as-built dwellings are just as good as those homes constructed under research lab conditions? Any comments on that?
I believe so. They are in constant collaboration with us. They pay attention to our results, and for instance, with one of the house builders, we have regular updates every 3 weeks about what is going on in the labs and how their houses are performing, and they often visit and see what we are doing and make changes and so on. So I would say yes, definitely, because otherwise, it would be, there would be no point to measure anything unless this is applied in practice, and I'm sure that is applied in practice.
Are there any other questions? Please do write them into the chat, or if you want to unmute yourselves, obviously, no problem. Yeah, and here we go. David Moore, excellent presentation, especially the savings percentage updates. Are the slides available? The slides won't be available, but we are recording the session, so we'll upload the session webinar video onto the UKAEE YouTube channel. So you can watch it, and we'll be doing that over the next couple of weeks or so, if that's okay, Lubo.
Yeah, absolutely, yes.
Thanks, David. Could I ask about the next sort of development? You mentioned the smart house, energy house, and smart IoT stuff, I suppose. How's that going, and when might we see that being set up?
Did you mean the actual gadget on the wall, the heat transfer coefficient?
You had a slide there was showing the different, energy house 2.0, and then the future energy houses coming out, I think, and you mentioned maybe smart homes, or it was something like that. It was an early slide.
Oh yeah, the future homes. So
yeah, I think so. And then there was
the future homes are happening this year. So that is happening this year, and I think anything below that standard will be, I believe, seen by house builders as not worth doing, because if some house builders are going for the future home standard and others are not, then the ones that are not are going to be not going to be competitive.
Fair enough, thank you. And then we have a comment here from Dara. Fascinating talk and a good insight into some vital research. Regarding the climate chamber, is it able to capture radiant exchange between the roof and the night sky? If not, is this likely to be significant?
Okay. Okay, so presumably we are talking about radiant exchange between the house and the roof of the chamber, representing the night sky.
I think that might be what is that what you're talking about, Dara? Things regarding the climate chamber, is it able to capture radiant exchange between the roof and the night sky? If not, is this likely to be significant? So yeah, maybe yes, is the chamber able to mirror the effect of a night sky?
I would say no, because the night sky dome has temperature that is several degrees lower than the actual air temperature. So if we're outside the night sky, it's going to be colder. That is not going to be a problem, because we can simulate houses under different conditions. So even though, let's say, if you have 15 degrees outside, if a house is outside, you have 15 degrees, and at night the sky dome will be 10 degrees. Okay, but we can reproduce all these conditions in the chambers anyway. So whereas we cannot reproduce the night sky temperature in the chambers at that very instant, we have the whole range of temperatures that we can test the houses under, and therefore we will know what happens when the chamber temperature corresponds to night sky temperature of a certain level. But because the loft insulation is always very significant in these houses, 270 millimeters, then the night sky temperature is not really going to be significant at all.
That's great. Thanks, Lubo.
Also, one more thing is when we talk about night sky in a kind of real life situation, it's not just the roof that exchanges the heat with the night sky. It's the whole house, because the night sky is a dome, effectively. So again, we can simulate any kind of temperatures in the climate chambers, and therefore night sky at let's say 10 p.m. Today can be simulated anytime during the day in the climate chambers.
Great, thanks, Lubo. I think we're at 12:01 now, so a little bit over, but I'm just going to put into the chat our email address. You can get a credit or continued educational units, I think they call it, like for the hour session that we've had for CPD. So I've just put the email address in the chat there. If anyone on the call is interested in us sending out something just to help you report on this on this unit, send an email and we can send you something out in the coming weeks. But otherwise, Professor Lubo Jankovic, thank you very much for a really interesting talk. I think, yeah, I really found it fascinating, and I think everyone else did. Really appreciate your time, and look forward to hopefully collaborating on some other project in the future, and meeting again. So thank you very much.
Thank you. Thank you for the invitation. It was a pleasure, and look forward to keeping in touch.
Great. Thank you. Take care, everyone. Thank you.